Hi, everyone. Hi, everyone. Thanks, everyone, for coming to the seminar today. So today, we're really excited to have Sherry come give a talk. So Sherry is currently assistant professor at NYU, and she's also a research scientist at Google DeepMind. So she's done a lot of really interesting work on the intersection of world models, as well as foundation models for decision making. Great.
Yeah, thanks, Elon, for the introduction. And hi, everyone. I'm Sherry. I'm very happy to be here to talk about this exciting line of research that I and my research group has been working on for the past few years. And this is around learning world models and agents for high-cost environments. So when we look at agents and environments for some background, usually we have some neural network parameterized agents taking actions that are executed in the environment, and the environment provides some next states or some reward information, and then the agent can self-improve based on this information. And just to ground these in some concrete examples, when the environments are some games such as Go, and the agent can learn where to place the pieces and optimize itself based on the outcome of the game. And then we have superhuman agents such as AlphaGo. Another example of agents and environments is large language models generating code that are executed in some terminal environment, and the execution outcomes are given back to the agent, and then the agent can optimize the code. And again, we see that LLMs are able to achieve superhuman performance in achieving gold medals at these ICPC international programming competitions. So I think it's almost fair to say that when we have a high capacity agent and a low cost environment, we kind of have already, as a research community, figured out how to achieve superhuman performance, for example, through reinforcement learning. And then by a high capacity agent, we mean deep neural networks, language models. These are things that are already pretty mature. So I would say like this low cost environment is really the bottleneck for really unlocking general purpose generalist agents for more diverse environments beyond game settings or coding settings. And if you look at examples I showed earlier, where we do have superhuman agents for playing the game of Go or for competing in these programming competitions, those are the cases where the environment interaction is relatively cheap, right? Where we have game simulations or program executions are pretty cheap in those cases for generating code. So really, the bottleneck for unlocking more agentic capabilities is in this low-cost environments. So for example, when are the low-cost environments assumption not true? Well, when we have robots interacting with the physical world, then the cost is definitely not low because, not just the time it takes to run robots, but also the safety constraints and so on. And even beyond physical settings, even there in virtual settings, we still have cases where the cost of interaction is quite high. For example, if we want to train agents to be able to conduct machine learning experiments, building models, running experiments, and this can take days to train a machine learning model. And these are still the cases where we don't have superhuman agents, replacing machine learning researchers necessarily. And when we go beyond virtual code generation, if we look at scientific domains, then we also have the situation where interaction is quite expensive. If we have some discoveries from AI and then we want to test these hypotheses by trying to make some new materials, for example, this feedback loop, again, is very expensive. So motivated by these particular examples, my talk will be looking at these three domains of these high-cost interactions. And for different domains, I'll talk about different ways for tackling, learning how do we build agents in these high-cost environments. And we'll start with how we can leverage world models for physical agents for building robotics. And after that, I'll switch gears a little bit to talk about for machine learning engineering agents, how we can modify existing RL algorithms for them to work better with these high-cost environments for MLE experiments. And lastly, I'll talk about how we can build systems of science agents so that we can actually accelerate scientific discovery despite the fact that scientific interactions are quite expensive. And eventually, I'll show you how these different, even though we're looking at three separate applications, like eventually they will come together, world models, RL, and system of agents. So with that, let's begin with learning world models for physical agents. So I think when we talk about world models, it's important to really define what we're talking about because nowadays world model is a very overloaded term. And specifically, what I mean by world model is this classical definition of a visual dynamics model. And in fact, people have already looked at this visual dynamics model even back from 2018 or even earlier. And in this particular setup, we have some dynamics model that takes some observations, such as previous frames of a game, and some actions, such as the keyboard controls that are given to the model. And what the model does is it basically just predicts the next few frames of what happens if we were to execute these actions. So these are some examples from these two papers back when people trained these models on these simulated game environments. And they showed that we can pretty much get very similar generated video frames that look exactly like how the games should look like. So then the question is, well, if there were already this world model research back then in 2018, then what is interesting about world models today, right? And I want to point out that there are two things that are very special that makes working on world models interesting. First is that we have internet scale video data, because back then, the only data set, because training a world model requires a lot of data, and then the only place where people can get a lot of video data is from these game settings. That's why most of these world models before was only training game settings. But now we actually do have access to internet scale video data with rich actions. And beyond internet scale video data, we also have figured out how to build these scalable video generation architectures with transformer backbones. And these are the two things that really enabled us to work on more interesting world models and that can actually model realistic real videos from the internet. So in this particular work, this is a kind of like a cross-institution effort in building this data set called OpenX embodiment. And then, this is one example of internet scale video data that contain rich actions. And so if this is the example of the internet scale video data, then for the scalable video generation architectures, what we can look at is, this is one example of the scalable video generation architecture. Of course, there are other architectures, but I just want to give this particular example because our set of work is built on this kind of infrastructure. And this is called like the diffusion transformers, DIT architecture, where essentially images. So initially, this architecture was developed for image generation, where the images are encoded into some latent space, and a transformer model is trained to predict the latent autoregressively. And then there's the decoder, for which, after a few denoising steps, decodes the generated latent back to the image space. And so what we did in this work called WorldGym is that we took this DIT architecture that was initially developed for image generation and applied it to video generation. And in fact, there are also concurrent work and earlier work that applied a similar technique, and such as the diffusion forcing paper, where we can essentially turn a DIT and then just continue to decode these intermediate latent for these future frames, and so that we can turn this DIT from image generation into video generation. And now what we can do is that the dynamics model can condition on some past frames and some future actions, and then predict the future observations in the image space. So what WorldGym did is essentially we try to train this robot world model by feeding this large-scale video action data set into this video generation architecture. And the data set is very heterogeneous in terms of the action space or in terms of the observation space. Nevertheless, we just represent the actions using a continuous vector, and then we represent the videos using image pixels in the image space. And so just by training this, the hope is that we can combine, using videos as a unified representation and just like feed all of these videos into this large transformer model, and hopefully we can get back like a general model that we can sort of like execute different controls in. And specifically, this is the model that we get in return. And what you can see is that there are some examples where we did some simple test, which is just we try to execute different kind of actions in this world model. So all of the videos you're seeing here are generated. And you can see that we can now start from any initial frame and then roll out the actions among different axes. So we can see like we can actually, in the world model, conditional actions, move the robot arm left and right, up, down, into or out of the page. Or we can also open and close the gripper. And we can do that also not just for one type of robot, but we can do it for another type of robot as well. And so you can kind of think like as if we're playing a game, right? Like we're pressing these different keys, we're moving left and right, but this is really where controlling this robot almost like very photorealistically. And what you can do is like you can actually scan this QR code, and then what it will bring you is to this website. I want to point out that the reason that this work is pretty interesting is because it's actually quite feasible for people in academia to work on this, because we trained this model using only 2 A100 GPUs. And then it's a model with 600 million parameters, but nevertheless, we can actually do a lot of interesting research with this model already. So if you do take a scan of this QR code, what it will bring you is to this website where you can actually try to look at what this world model might, you can actually try to interact with it in real time. And so basically you can select different initial frames just by clicking on, there are many more frames, right? So it's showing like it's really generalizable. It's not really limited to a very specific set of scenes. You can really pick any initial frame. And then you can try to press different keys, like there's keyboard instructions here. So we can try to close the gripper. Let's close the gripper. And then after that, we can try to like, so the GPUs are running in the backend, and this is actually running live right now with the 600 million model. Is that a question? Okay. Okay, cool. Yeah, so let's say we can try to move the robot gripper to the right. It's generating, it moved a little bit, maybe to the right again, right? And let's try to bring it out of the page. So you can see that, it's okay. Here's when hallucination does happen, right? So, I mean, but the point is that this is a 600 million model that was trained on, 2 A100 GPUs, but nevertheless, it's able to kind of, allow you to interact with it in real time. So we can try to, sweep the beans on the table by, move right again. It's a small model, so a lot of hallucinations does happen, but it's really showing you that, and the code is open source, by the way. Like you can just like click on this link and try to like go to the GitHub repo, and we've already verified many times, like you can download the model and reproduce these results. Okay, so it's interesting that just by feeding this rich data sets into this large model, we could actually get back a somewhat controllable robot world model where we can press different keys and control different robots of different morphologies, at least in the visual space. But I think the real question is, how is this world model useful exactly, right? So because I think the usage of the world model is the best, evaluation, defines the evaluation metric, and it also defines the feedback loop for improving the world model. So one concrete use case of world models is to evaluate policies. Because if you look at how currently robot policies are evaluated, they're either run in the real world, which is very time costly, and also has safety concerns if people break the robot arm. And also there's a big reproducibility challenge because every robot lab has slightly different setup. And when they run policies, which are highly dependent, highly sensitive to the initial frame, it's really hard to reproduce results from another lab. And alternatively, what people have done in the past is to use simulated evaluation to try to run robot policies in simulators. But then simulators have the issue of both visually not looking realistic, and also the simulating some of the difficult interactions like soft object interaction in the simulator is not very easy. And besides, like simulator, it requires some kind of programming, and then whenever you have a new scene, it's not very general. It's not super clear how you can turn this new out of distribution new scene into a simulator. So now, since we've trained this world model, and what we can do is we can just try to overcome the challenge of evaluating robot policies in the real world. What we can do is we can evaluate these policies in the world model. And what we can do is we can take these policies, and these policies generally take some initial image observation and some language instruction, and it predicts a sequence of actions like delta x, delta y of how to move the gripper. And we execute these actions in the world model, and usually these actions are predicted in chunks, right? And then we would give the last frame generated by the world model back to the policy, and then the policy can continue generating the next sequence of actions until we have the full rollout from running these policies in the world model, and then we can give this video to a reward model. In this case, in World Gym, we basically just use vision language model, pre-trained vision language model as a proxy reward model, and then to tell us whether this task is successfully completed or not. So this is roughly how the rolling out the policy in World Gym looks like. And here are some examples of like what happened when we try to roll out these different policies, right? So these different policies are developed by different institutions, and it's in the past it's really hard to compare them. But now with the world model, we can just like very easily look at how they might perform differently. So for this task of putting the eggplant into the pot, the OpenVLA policy worked the best, and then the Octo policy, which is like a slightly earlier version. Also developed by some people from UC Berkeley. Like OpenVLA was developed from Stanford. And we see that the Octo policy actually kind of like gets stuck at like picking up the eggplant. It actually doesn't quite put the eggplant in the pot. And then this RT1 policy from Google is much earlier, and it doesn't seem to do something reasonable. Actions were predicted too out of distribution, and even the world model starts to hallucinate. But nevertheless, we can still see that very clearly which policy is performing better than the other policies. And now, not only we can evaluate, that particular robot, we can also, because these policies are supposed to be generalist policies, meaning that they should be able to control any arbitrary robots that they're trained on. So this is an example where we can, now we can switch gears and look at different frames, initial frames with different robots, and we can try to roll out these different policies again. And for this simpler task of closing the drawer, it seems like all of the policies are doing a reasonable job at completing this task of closing the bottom drawer. So those are some, I think qualitative evaluations. So just by rolling out the policy in the world model, we can immediately tell whether, the policy is doing well or not. But furthermore, we can kind of like compute some of the success rates according to this framework of, rolling out the policy in the world model using VLM as a reward, and then compare that policy success rate to the success rate of running the policy in the real world. So we got the policy successes from the OpenVLA paper, and we plot them on the table. This is aggregated results in terms of the success rate. And then we also compute the success rates predicted by the world model plus the VLM reward. And we found that the world model success is actually very close to the real world success, maybe with 3% difference at most. And more importantly, the relative rankings among the policies, like OpenVLA performs the best, and RT1 and Octo perform much worse, is preserved. So this is just to validate that, okay, we can use world models as a proxy of the real world to evaluate policies, but world models actually have like a lot more promise in terms of creating, yeah.
So test that the model.
Yeah, exactly. So in order to plot this, we took the initial frame from the OpenVLA paper, and then just give that frame to the policy and then the world model. So they're starting from the exact same initial frame and rolling out, and then the exact same number of trials as the real world. Yeah.
And like it's the same, like it's the percentage you're showing here, or the same factor.
Yes, so the evaluation tasks are exactly the same between real world and simulated world model. That's your question, yeah. So like, for example, like this is one of the evaluation tasks, like picking the eggplant. So this initial frame is taken from the OpenVLA evaluation. This is a real frame, but the generated frames are from the world model. Yeah. Yeah.
Is the world model fixed? I mean, it is trained for specific tasks.
Yeah, so the world model was trained on this diverse data set of this OpenX embodiment data set. So it contains, a large portion of the OpenX embodiment is this bridge data set, which is this particular example. But it also contains some other data sets, such as this Google robot. Like this robot is also from this data set. Yeah. So basically, there's a training stage for the world model. As once we train the world model, action condition video generation, we fix that. And then we just execute policies in this pre-trained world model and get the videos and get the success rates and use the world model for policy evaluations.
It perform less useful tasks. Like you cannot ask it anything.
So I mean, so it's not conditioned on language, so it's not conditioned on tasks, it's conditioned on action. So the hope is that, this is exactly the example we're showing here, which is, like if you had trained it on sort of diverse robot controls, now you can kind of like press different keyboard controls to really interact with the model, and you should expect it to generalize in terms of how the controls should look like, because it's not conditioned on task. But it is true that it's only trained on these robot morphologies. So if you have a new initial frame of a robot that the model hasn't seen before, it's probably not going to simulate interactions very realistically.
So it's not conditional on the task.
It's only conditioned on the actions. Yeah. So the actions are end effector poses, like the XYZ locations of the grippers. Yeah. Yeah. Okay. Great. So not just like world model is like could be used to replace the real world or substitute, at least as a first step for evaluation. I think world models are also have the promise of like being able to create very novel scenarios for evaluation, right? So in this particular example, what we did is that we took a real image frame and we used Nano Banana to edit the initial frame by adding a new object, which is the orange. And then so you can see this orange is added. And then we create a new task, which is now we're asking the policy. So the original task, that was used to train the policy was to pick up the carrots, but it has many different tasks. It didn't have this particular task of picking up the orange, so that's why we want to test. Okay, if the policy is actually truly generalizing to different tasks, it should be able to complete this new task. But then what we found is that the VLA policies, OpenVLA, which is what we are evaluating here, actually doesn't really complete this new task. It overfits to the task of picking up the carrot. And then we could also kind of like simulate some of these adversarial settings where we use the image editing model again to place like a computer screen in this kitchen environment. And then we ask the model to pick up the carrot. And then again, like for some of the cases, the model will actually, decide which way to go and eventually pick the carrot that's in the computer screen. But this is a goofy example, but it's really showing that you can really use the world model to simulate some of the long tail distributions of what might happen in people's household, and then try to assess policy performance in these, extremely long tail and rare distributions. So in addition to evaluating these out of distribution tasks, we can kind of like use the world model as like a debugging tool for the policies, right? So the question we're asking here is that are VLA policies good with colors? Are they good with shapes? And do they preserve internet knowledge about Taylor Swift and Snoop Dogg? And so again, we use image editing tools to just place, papers of different colors in the first example. And we found that the VLA policy is actually pretty good with colors. And they always consistently pick the right color when we specify red or blue. But then they're less good with shapes. When we specify pick circle versus pick square, it's almost 50-50 which direction the policy will go. And our hypothesis is that in the VLA fine-tuning data, because VLA are usually fine-tuned from VLMs, and in the fine-tuning data, sometimes we actually do see the color annotations in the text description, like pick up the yellow banana, but it's a lot more rare to see shape description, like pick up the round apple, like that rarely exists. So as a result, the policy doesn't have too much of a knowledge of shapes. So they would actually, pick the wrong shape. And what's interesting is when we, say pick Taylor Swift, again, 50-50, the model will go either direction. And I think this is saying something that's quite interesting about vision language action policies, which is because if you think about it, if you ask a vision language model which one is Taylor Swift, you're probably going to get the right answer. So it's almost like by fine-tuning a pre-trained vision language model on these action data set, the model actually lost some knowledge about which one is Taylor Swift. So it's a question of like whether, fine-tuning vision language models using action data, the VLA approach is really the best approach, because it does seem like because the action distribution is so narrow, then there is loss of internet scale knowledge that was already in the VLM. And another kind of like thing I wanted to point out is that maybe for this picking Taylor Swift example, this is more of a post-training problem, like as opposed to a problem, because we're never going to collect enough robot data for all of the celebrities that you write. So, but then it's pretty easy to tell by looking at this policy rollout that actually the policy moved to the wrong direction. So it's more like it's one of those cases where it's easy to verify, but it's hard to collect data for. So in some sense, and also the samples are 50-50. We do see some cases that the arm does move to the other direction. So it's a perfect, I think it's a perfect setting for post-training for using RL fine-tuning with the reward information that the policy did something wrong. Okay, so that is actually a good bridge to what I want to talk about next, which is, so there's World Gym. We named it World Gym because it's supposed to be, a simulated world that can be, used to evaluate and train policies. And the world gymnast is actually using the world gym model that we talked about earlier to actually train robot policies. So what we did is we again took the OpenVLA policy and we just simply have the policy interact with the world model and then use the vision language model as reward and get successes and failures. But now, in addition to just use them for evaluation, we actually pass the successes and failures back to the policy for some gradient updates through policy gradients, right? So in this case, the A is just the advantage function, which is a way to describe based on successes and failures. So if it's a success, then the likelihood of that particular trajectory is going to be upweighted. If it's a failure, the likelihood is going to be downweighted. And that's a simple way to interpret policy gradient updates. So the particular algorithm we chose was GRPO, but I think it's not the key message here. The key message is you can use the world model to do rollouts and use the reward information to run RL fine-tuning for the policy. And there are a few advantages for doing this, right? So one is that you can really train on any frame that you have from the data. The data usually contains some kind of teleoperation or running the robot policies. So it's actually very diverse. And you can really treat any frame from your data set as the initial frame for training this policy to start from any frame in the data to complete this task. So you can maybe get some kind of failure recoveries from just RL fine-tuning from an arbitrary initial frame in the data set. And then there's also, you can construct these novel tasks that I showed you earlier, right? By editing the image. And all of a sudden, you have a lot more tasks, like picking the orange, which wasn't in the initial task before. And you can also create new language instructions from an initial frame. There might be multiple objects, and you can really create many different tasks. And because all you need, right, for the world model is really just the initial frame and for the policy is some language instructions. So you can create many more tasks for RL fine-tuning. And that's also one of the reasons why GPT-3 didn't really work until we had RL post-training, because people can just now use a verifiable reward, which is a lot more scalable, and then having many different prompts, and then running RL. Same idea here. So basically what we did is we had some of these initial frames from the training data sets, and we run RL fine-tuning on this particular initial frames from the bridge data set. I think what's more worth talking about is the evaluation setting for world gymnast. Yes, there's a question.
Is your reward a binary?
Yes, the reward is binary in this case. Yeah, we actually did something about partial credits, but then during the RL process, we hope that could provide some dense feedback. But then we found that the model ended up the policy ended up just the reward hack the partial credits and not actually making full progress. Yeah, so we ended up just using the binary reward at the end.
So then with the VLAN, only to see the last frame.
We actually do give it a few frames downsampled, and not all of the frames, but downsampled frames to the VLM. Yeah. Right, so I wanted to point out the evaluation setting, which because we want to be as objective as possible in this evaluation, right? We didn't want to just run our own robot because we might be biased to think that our RL policy is better. So we ended up using this auto eval platform, which is a work from Berkeley that they would have some kind of reset policy that automatically runs in the background. So they can so all we do is submit our policies to this platform and watch the live feed that actually comes back. So this is real robot evaluation, but we don't have control over how these evaluations are run, right? So we just submit the two versions of the policy. One is the policy without RL fine-tuning. Another is the policy that was fine-tuned using RL in the world model. And these are the evaluation tasks that were supported by this auto eval platform. And these are tasks including open the drawer, closing the drawer, put eggplants into the blue sink, and put eggplant from the sink back to the yellow basket. So these are the real world rollouts of what these tasks look like. So then what we found is that we compared to some baselines, which is more of running RL in a simulator, in a software-based simulator. And in this case, we compared to Simpler, which is a real-to-sim framework where they take a real image and have ways to kind of generate the code that simulates this environment. I will show you some examples of Simpler later. And what we found is that generally speaking, running RL in the world model is actually much better than running RL in the simulator for pretty much all of the tasks except for this closing the drawer, because the closing drawer task is very simple. And it turns out that having like a real-to-sim simulator was, somehow doing well. But for all of the other tasks, especially pick and place, for putting the eggplant and so on, the world model actually turns out to be a lot better than running RL in a traditional, in a handcrafted simulator. And we also compare to some other iterative SFT methods because, after this action condition video generation world model became more of a research interest to many labs, there's other work such as control world, which uses the world model to roll out the policy and then to select successes and then use those successes to fine-tune, use those successful actions to fine-tune the policy, which we call like iterative SFT. So just to make sure our comparison is comprehensive, we also compare to some of the iterative SFT methods, and we found that, again, for generally speaking, RL is better than just the SFT model or the iterative SFT model because the model can now learn from failures as well, in addition to just filtered successes. Especially for these pick and place tasks is where we see the most amount of the benefits. So we also did some additional experiments because I think this is the current mental model I have for thinking about world models for robotics and agents, which is we have this Dyna style setup where the agent interacts with this world model learned dynamics model at a much higher frequency to self-improve, right, through reinforcement learning. And occasionally the agent will execute these actions in the real world and for evaluation or for data collection. And then this additional real-world data should not just only be used to improve the policy, it should really be also used to improve the world model. And then so that the policy can, interact with the improved world model to improve itself and then occasionally collect data again. So this is pretty, there's, Dyna is a very classic algorithm that, that proposed this setup. And we just simply applied this setup in like video-based world models with visual language action policies. So this is an example of what replaying the same sequence of actions as the ground truth, but one in the real-to-sim simulator called Simpler, and the other is in the Dyna improved world model. And we see that this is what the ground truth looks like. And in real-to-sim, it actually is quite far when we play the same sequence of actions. But in a Dyna improved world model, where we updated the world model using additional data from this auto eval environment, we could actually get the world model to be a lot more adhering to the ground truth than the real-to-sim approach. And I just want to point out, like, having a parametric world model is just a lot easier to continue fine-tuning them whenever we have some real-world videos than to hand engineer some real-to-sim pipeline to be able to simulate this new setup. And furthermore, we show, like, after we fine-tune the world model using additionally collected data from the setup, the policy we can, because of this Dyna style updates where we use the improved world model to train a policy, we can get the policy to actually perform better when we have online access to this additional data collected from the environment. Okay, so to sum up the first part of the talk, we really discussed, how do we sort of build the world model for physical agents. And I know there are many different ways nowadays for people to build world models. Like there are these 3D-based approaches. There's also these latent JEPA-style approaches. Here today, we only talked about a specific approach, which is action condition video generation. I think it's important to think that there are other ways. Maybe some approaches are easier to scale than others. But I think the general concept of like using a learned model where we can sort of just like feed diverse data, large-scale robot data in a single model, and then as a result get back some kind of like generalizable virtual controls of different robots in the world model is kind of like pretty common, shared across these different approaches to world modeling. And really the usage of the world model should be grounded in evaluating policies in these low cost and safe and reproducible policy evaluation settings. Now there's no more the problem of different labs running different robot experiments because all the policies will be executed starting from the same initial frame. And lastly, we show like, RL in the world model can actually work better than RL in a simulator. For manipulation, I think this is quite exciting because we know simulator work pretty well for locomotion and for navigation, but for manipulation, we always have this sim to real gap where the policy improved in the simulator, in a software-based simulator, but the real-world robot success didn't improve. So I was also pretty surprised at this world gymnast results where we trained the policy using RL in the world model, and it actually translates to better policy performance on the real robot. Okay, so we spent a lot of time on the world model for physical agents. So I want to switch gears a little bit to talk about, because there are many high-cost environments, and we're going to switch gears to look at how we can, use RL to train MLE agents when the interactions are very expensive. So to just introduce you the background of MLE agents, usually the problem setup is that we have some problem, a machine learning problem, such as predicting obesity risk. And we have some data set from, for example, Kaggle challenges, and these data set contain some training data and test data. And then the setup is that we're going to give all of the problem descriptions and the data set to the LLM agent. And then the agent will propose some high-level plan. And if you look closely, the agents are generally these days pretty good at proposing these plans. Like they will propose things like what models to use, gradient boosting, where to load the training data, what kind of loss to use, binary classification, and what kind of evaluation AUC curve to use, and eventually where to save the test predictions, right? And then these high-level plans will be turned into low-level Python code for loading data, building model, training model, saving results. And finally, these code will be executed in some execution environment, and then the traces and the results will be given back to the agent. And then the agent will just keep on doing this in the loop, right? Seeing the previous execution results, trying to optimize its code and plan, and so on. And then we just let it run for a long time. And then the ultimate goal is to optimize the performance of the agent on like the generated modeling code on some test split of this machine learning problem. So if you look at the state of the art, a lot of the research really goes into like building agent scaffolds, which are just collections of prompt organized in using some kind of software structures, right? And this is a particular case, it's called AIDE, but what it does is like it has a collection of prompts, such as asking the agent to come up with a new solution for the ML problem. And it actually maintains some kind of memory, right, using some kind of data structure. In this case, it uses a tree where each of the node contains a solution and the execution outcome. And then the edges are basically, what's the previous solution. And the scaffold can prompt the agent to maybe debug a previous solution, in which case the edge will be added. Or it can also ask the agent to improve a previous solution if the previous solution is not buggy. And then what happens is just like for hours and hours, we'll just let the agent scaffold to, take control and build, just generate solutions and over again, and hoping that just by, doing this in the loop, the agent can develop better and better solutions. And this tree is like serialized and, given to the agent as context. So one interesting observation we've made is that just through prompting, we actually could not get better performance after a certain number of hours. Right, and the issue could be because of the agent couldn't really utilize the long context of experience. I think there's generally a lack of the ability of turning experiences into actionable knowledge and actually to come up with better solutions. And if you think about it, like really the problem is that there's no gradient updates. Like through search, like in this tree, maybe we can find better solutions, but the agent hasn't really learned in terms of how to better solve this problem. So yeah, the agent is not actually getting better at this task, right? Even though it's like searching for better solutions, but the gradient for the model hasn't really been updated. So then like the proposal is just, okay, since we have the ground truth reward information, which is nice for these MLE settings, why don't we just do policy gradient updates to fine-tune the LLM agents to come up with better ML solutions? So instead of only giving the execution trace, we actually update the parameter, again, grad log pi times the advantage function, and use policy gradient to update the agent. So when we naively apply the policy gradient RL algorithm, we actually noticed something that's quite interesting, because a lot of the modern like RL for LLM infrastructure, like there is like this asynchronous RL setup, where a bunch of actors execute a bunch of actions, and then whichever action that comes back first will be used to update the policy, right? And what we found is that during the RL training process, initially the agent actually comes up with some more fancy solutions, such as doing some kind of grid search of the hyperparameters or using random forest, and then they actually do tend to take a longer amount of time, like 100 seconds and so on. And then the performance in the parentheses are like the performance on the test split are like the performance for this task. And what we found is that during the RL process, basically the agent just chooses faster and faster solutions despite these solutions being suboptimal. And the reason is pretty simple in the sense that because the actions take a different amount of time to execute, and then the actions that execute faster, it just ends up being sampled a lot more often. And then there's this frequency bias, and faster actions just gets updated a lot more often than slower actions. So that's the first issue, which is this variable duration action. And then the second issue in this practical MLE settings, which is the sparse reward setting. Because if we're using the performance on the test split as reward to train the MLE agent, then for two solutions, one that failed at data loading, and then another solution that's almost successfully completed the task, but failed at the last step of saving the predicted test labels into the right location, then these solutions, they both achieve reward 0 because they didn't successfully produce a valid test labels. But then nevertheless, they made different progress, right? So there's this lack of intermediate supervision. So to overcome these two particular issues, we have this particular paper on reinforcement learning for MLE agents, where we look at the naive policy gradient update objective, and we see that this is more pointing at like a problem where maybe like fundamentally the MDP formulation is limited, right? Because we assume that we only make decisions at these step boundaries, but in an MDP we never consider the amount of time it takes to execute an action. There are better sort of theoretical frameworks for this, such as semi-MDPs, continuous time discrete intervention, but those are sort of, those are quite old, and there aren't a lot of algorithms that were developed for those. So we're more just looking at, okay, if we have this MDP formulation, how we can overcome this issue of variable duration action. And it turns out that there's one simple update, one simple change that we can make to the update rule, where we simply just weight the policy gradient update by the amount of time it took the action to execute. And we have more results in the paper in the appendix, you can see. But basically, this actually leads to an unbiased gradient estimate of the policy gradient. But it's a very simple change, and it's actually balancing, right? So for the action that takes a really long time, it's seeing a lot less frequent. So the policy gradient will actually have a bigger weight than actions that actually run a lot faster. And that's how we fix the variable duration action problem. And then for the sparse reward problem, what we did is what we call environment instrumentation. So in this case, what we did is we took the code, instead of directly executing the code in the environment to get reward, what we do is we first feed this code into another copy of the language model and ask the model to please insert these print statements to the right locations. And then what we can get is this instrumented code where we have printed progress, like loaded data, defined model, trained model, and so on. And then what we can do is we then run this instrumented code, and we can now parse out the printed results from the terminal and assign these partial credits during this training process. And I want to point out that it's very important to use a separate copy of the LLM as opposed to using the same LLM that's being gradient updated. The reason being, if we actually do assign these partial credits to the original model, what the model will do is reward hack, and the model might just end up generating a bunch of print statements without actually doing the task that's supposed to be captured by the print statement. But when we use a separate copy of the model, inserting print statement is actually a pretty simple task. So then the model has no incentive to just generate a bunch of repeated print statements. So with these two changes in implementation, we were actually able to get a much smaller model like Courant 2.53b plus RL to continue improving the performance on this particular task, like leaf classification, than some frontier model plus this complicated agent scaffold, especially if we give the model enough time, right? you can see that the smaller model actually initially performs much worse than the frontier model, but eventually, because of the gradient updates, the smaller model do catch up. And then this is looking at many different tasks. In general, a very small model plus RL can outperform. At the time, we used Claude 3.5 SONAT as the SOTA model, and it could actually, outperform these complex frontier models with complex scaffolds. And here's an example of what environment instrumentation does to the RL process, where without environment instrumentation, we see that the reward actually grows a lot slower than when there is environment instrumentation, where we get these partial credits. So the model can actually learn to, find the right place of the data, because it could really fail from any steps. It could hallucinate the paths for the data set to load from. And here, using these partial credit, the model can actually gradually learn, like loading the data from the right place and building models and so on. Okay, so that's pretty much the second part, where we talk about RL for MLE agents. And I think the thing that's worth pointing out is that in these more emerging applications of LLMs beyond math and coding, in these new applications, there are new challenges that existing formulations of the problem, including MDPs and including these algorithms that assume action execution takes a constant amount of time, are no longer applicable. And this is really opening up new research areas, including redefining how we should maybe revisit some of these classical concepts, such as semi-MDPs, for developing better algorithms, or algorithms that actually fits the current application needs. And then I think the concept of environment instrumentation also applies to beyond MLE settings. For these very high-cost actions, we should try to get as much information as possible from these high-cost actions, because they're high cost, right? So the more instrumentation we do, the more information we get from running these high-cost actions. And this is just one example of inserting print statements, but there are other ways to instrument the environment so we can get more information. Okay, so that's RL for MLE agents. And lastly, let's look at how we can build system of science agents to perform some scientific discoveries that could take a very long time. So I think one of the intriguing research topic in AI for science is really in this domain of language to structures, because this is something that computational scientists don't have, right? If you work on something else, they might already have some tools, and we have to compare why is generative models or why is AI better than the tools they already have. Whereas for language to structure, they don't have such a thing, but it's highly useful because it could enable lay people to design materials by specifying these high-level constraints. And then going through these intermediate steps, such as generative models or some discriminative models or some computational tools, the output is some kind of final structure that is proposed by this pipeline. And the scientists can just look at this final structure and decide if they want to synthesize them or not. So if you look at the existing computational methods and what their limitations are, again, they're pretty expensive in terms of the compute cost. First of all, so this is AIRS, which is ab initio random search, which is one computational methods that people use to discover novel materials. And how it works is basically they have experts come in and design the compositions. So the expert will design some kind of chemical formulas. And then this AIRS framework will take these formulas. It has some algorithm to guess the initial volume of the structure, and then initialize some random structures given this composition. And then it runs the DFT calculations to relax these structures. And when they guess enough of the random structures, they end up getting different looking structures. But again, this is quite expensive because the convergence rate for the DFT is actually quite low, because these are from random guesses, right? So a lot of things are being wasted during this process. So what we can propose here is that so in this particular work called Generative Hierarchical Material Search, GEMS, what we propose is that we can actually use a system of AI agents to break down this problem of language to structure. To, first of all, maybe we have language agents that have absorbed internet scale text-based knowledge from nature papers, from textbooks, and so on. And usually this knowledge stops at some intermediate level, such as the chemical formulas, right? So you see the chemical formulas in the textbooks, but you don't see the exact structures with XYZ locations of the atoms. And usually those low-level details lie in some other materials database or protein database, for example, and they are usually present in continuous format, like in the form of XYZ locations of the atoms in a 3D space, right? So what we can do is that we can actually train two separate agents. One is, a language model agent that can talk about science, that can propose formulas, and another is this low-level diffusion model that maybe given some intermediate formulas that predicts the low-level structure of what the structure should look like. And once we have these two components, what we can do is we can actually compose together the high-level agent and low-level agent. What we can do in this particular work is that we simply ask a language model to take this language instruction from people and propose intermediate formulas. And then, of course, we can do some checks of instruction following. And then until we find some good formulas, and then we use these formulas to condition the diffusion model on these formulas and predict additional structures and use these additional computational tools to verify whether these structures actually satisfy constraints such as stability and various properties that material scientists care about. So, and when this is the framework that we have, this hierarchical, search, we can actually narrow down the search space, right, pretty effectively just by using language and use the formulas that are actually satisfying the user's constraints. So, yeah, so what we found is that basically through this, this is basically first looking at, okay, so how do the generative model proposed structures compare to more classical computational material structure, this AIRS framework that we talked about, in terms of generating sensible structures that can converge during the DFT process, right? So we looked at the convergence rate of AIRS, which is computational methods, and then this UNIMAT, which is before we do the hierarchical search, we train this diffusion model, right, which is an end-to-end diffusion model for predicting the crystal structures. And we found that the diffusion model actually have a much higher convergence rate than the traditional computational methods. And not just that, diffusion model, generative model proposes something that can converge at a higher rate, but also the formation energy of the structures proposed by the generative model actually is generally lower than structures that are proposed by these computational methods, which is desirable because for materials discovery, you always want materials that are stable so that they can exist in many different conditions. And so another interesting finding is that because we have this hierarchical search process of generating formulas and conditional formulas to generate the structures, we can actually scale up inference time compute just by generating multiple formulas per language instruction and then generating multiple structures per formula. So you see that when we scale up the number of language branch and then the number of structure branch, we're able to get lower and lower formation energy and better materials according to DFT calculations. So people did a lot of this scaling up test time compute for language models, but the same idea holds for AI for science or using AI to discover better structures. So, and then what we did is that we took this GEMS generative hierarchical material search framework. Yeah.
What is the number of branch? What's meant by number of branches?
So the language branch here means like given one text prompt, how many formulas do we generate? And then the structure branch means that given a formula, how many structures we generate using the diffusion model. And the language branch is like how many formulas do we generate using the language model.
So 25/100 means 2500.
Yeah, so yeah, exactly. Multiply them. Right, so basically and then what we did is like we were trying to find applications, right? We had this generative hierarchical search framework that does seem to give us better and better structures, and then we try to see if we can actually help scientists. So for this work, we collaborated with people from UC Berkeley, Omar Yagi, and he actually recently got Nobel Prize for this MOF, not for this paper, but he did a lot of work on discovering this called metal organic frameworks, which are structures that are half organic, half inorganic. So it's like organic, it's like metal elements connected by inorganic linkers. And these materials have nice applications in like storing toxic gas and things like that. things that I'm not familiar with. But nevertheless, we kind of like used the framework, generated some structures, and had these scientists look at the structures. They're like, oh, interesting. These are the things that we couldn't find through computational methods because we have this nice compositionality, which I can talk about in the next slide. But here, the takeaway is that if you look at the rate, it's not ideal. Like we generated 20,000 structures, and only 2,000 of them passed screening. And the screening is basically using some of the computational tools that these scientists know about to pick out the good ones. And then, among these 2,000 structures that pass the screening, they have domain expert look at them and select the ones that they think should be synthesized. And of course, among the ones that they selected, only eventually 5 of them were actually synthesized. And these are the examples of the final synthesized structures. And these are the structures that the model, generative model originally proposed. And these are the structures that what they look like under the X-rays. And so, yeah, if you look at the rate, it's really not that high, right? 5 out of 20,000. But the idea is that all of these intermediate steps, maybe except for this is selecting, which is expert knowledge, which is quite expensive, but just generating a bunch of structures or running these computational tools, they are just compute, right? That can be relatively cheap. So, and for discovery, really is like when we generate thousands, as long as one of them is successful, like we can consider that as a big progress, a big step forward. So I do want to talk a bit about like what really made this collaboration successful. I think is the idea that similar to when we talk about world models for robotics, we have just pixels as a unified representation, so we can really feed in data sets of different robot morphologies or even data set of human hand. And in this case, we also, atoms in the 3D space, right? We just use that as a unified representation to feed in organic data set, inorganic data set from chemistry, biology, material science, right? So we get a generative model that is actually, cross different disciplines as opposed to these, human-defined boundaries of organic and inorganic. Because eventually there might be materials that are half organic and half inorganic that has nice properties, right? And then the reason that we can do this is because we have this compositional generalization that we've seen this in image generation quite often, where we can generate images of astronauts and horses, and because of this text conditioning, and maybe there are also images of kids riding horses, right? And now, so we learn the model learns the relationship of riding, and now we can generate a highly photorealistic image of an astronaut riding horses. And same idea here, which is you have data that are inorganic, and you have data that are organic, and you use a unified representation, which is pixels at the top, but atoms in the 3D space at the bottom. And now you can actually use some compositional generalization because of the text conditioning, the formula conditioning, to get some kind of compositions similar to astronaut riding horses. And I want to point out that the generalization is different from the kind of generalization people might expect from computational tools, which usually is pretty local, like because the tools, DFT calculations and so on, require some kind of local approximation. And you can think of like these are like local in the data manifold or compositional manifold of formulas. If you have formula AB, you have formula BC, then you might be able to generalize to AC. So the axes of generalization for generative models is actually quite different from these computational tools. Okay, so just to revisit what we talked about in building the system of science agents, I think that it is quite expensive still to run these experiments to try to synthesize novel materials. But nevertheless, when we have this hierarchy going from text descriptions to intermediate formulas, we actually really narrow down the search space quite a lot. And then, using these computational tools to further narrow down the exact structures that need to be looked at by people or to be synthesized. This is already generative models being able to help us narrowing down the search space. And then I just talked about in the previous slide where I think generative models, AI, offer a different axis of generalization, which is oftentimes compositional compared to these computational methods, which is oftentimes more like local generalization. And then lastly, like this idea of like unified data representation of atoms in the 3D space really allows generative models to be trained in data sets from different disciplines, and that turns out to have nice benefits for these more exotic discoveries that are cross-domain. Okay, so It seems like, we talked about three very different things, right? From robotics to MLE agents and finally to science. But I just want to say that, a lot of the things are actually shared across these domains in terms of learning world models and agents, right? And they all have the nature of like being pretty high cost. And in terms of the outlook, some examples are, for example, I think we can think about for these high cost interactions, right? What would be world models look like? So for this MLE example, we didn't really talk about how we can learn models of execution, right? We only talked about how we can mitigate the issue of actions taking a different amount of time. But a very different approach would be, since that we have run so many MLE experiments and all of them have experiment logs, can we train a model that predicts the experiment log without running the experiment? And there's some kind of like code world models that's developed at Meta, but similar idea, I think world model is the most useful when the execution is very expensive, right? So for code, if the execution is cheap, by all means, maybe just run the execution, run the action. But when the action requires, days to train a model, we probably have this dyna setup where it takes forever to, execute the actions. So the data is very valuable. We should accumulate the data so that we can train a model of cost and also model of information from the environment. I think like maybe model of information from the environment is like, what might the loss curve look like for this particular ML code? And so to have like the model of the cost will also enable agents to do more intelligent decision making, right? For example, we can have the agent generate a bunch of solutions for ML coding, and then it can also estimate how long is each of the solution going to take, and the agent can maybe try to first execute some faster actions to make sure like the data is loaded from the right place, like similar to like an actual ML engineer, right? To do some debugging without a huge model size, and then gradually, move on to like the more higher cost actions. So I think like trading off, right, the time spent in RL training, sampling, and then the time spent in running the actions, like making more intelligent decisions between how to spend the time is kind of like the next frontier for MLE agents. And again, for science agents, I think there's also kind of like interesting research topic around world models for science. And one example, as some people are working on models of molecular dynamics simulation. So usually, people will run some computational tools, DFT calculations, and so on to simulate this molecular dynamics. But again, like the locality, like these tools only work in very local perturbations. So as a result, people oftentimes are interested in these long time scales, which is what if you run simulations for minutes, hours, even days, right? And then the difficulty there is that it just takes too long to run these simulations. But then like once people do run the simulation, they can save the data and they can train a generative model or a world model dynamics model to predict into the future at much more coarse-grained time frames, right? Similar to when we generate video frames, we can concatenate all of the actions and generate the image frame that's like 50 steps away, right? So similar to the similar concept here is that we can, train a molecular dynamics generation model such that it can actually skip the time frames and be able to simulate things that are at a much higher, much longer time horizon. And then there's also, I think, interesting research around, there's also the sim to real gap, right? Which is not just in robotics, but in science also when people do computation versus what actually happens under the microscope. So then the idea is, well, if there's so much microscope data taken on a daily basis from these scientific labs, can we essentially train some model that predicts what things might look like in the microscope as a form of video prediction, right? So this is some initial results where, for this particular example, so there's an electron beam that's shooting at the sample, and then the atoms, in this case, some silicon and some carbon atoms will end up moving to some new space. And when we have enough of this data, what's showing here is that the predicted next frame under the microscope looks actually quite similar to the ground truth next frame. So this is kind of like using expensive microscope data to learn a world model that predicts what the samples might look like in the microscope. So I think these are all pretty interesting research areas around world models for engineering and for science. And then, for this hierarchical approach, you already saw how we can use it to, narrow down the search space and do more intelligent decision-making for science. And you also saw, like, for MLE agents, right, like generating plans and building this memory of high-level plans followed by low-level executions. And for the first, under physical agents, this is the work called video action planning, where again, you have the hierarchy of having some high-level policy predicting in the text space what should happen next, and then in the video space of actually generating the visual outcomes of this text and being able to do long horizon planning there. So this hierarchy, again, is sort of present across these 3 different applications. And with this hierarchy, we can do hierarchical search and planning, and even hierarchical reinforcement learning across these different domains. And ultimately, maybe when these things come together is, when you have, physical agents that you can develop and that combines robotics and this kind of experimental, designing experiments and that are being deployed in these scientific settings on science. So maybe this is like one of the ultimate goal, combining robotics, AI for science, and not MLE in this particular case, but still like some kind of experimental agents that can design experiments. So with that, I would like to thank all of my collaborators, including people from my group at NYU, and also many collaborators from Stanford, Harvard, MIT, and Google DeepMind as well, and UC Berkeley. And with that, thank you for your attention, and I'm ready to take any questions. Yes.
I have 2 questions. The first one is regards to world models. It's more of a speculative question. I guess with like the more unguided generation of world models, let's say Genie or other type of models, how can you see world models being used to sort of generalize across different robotic tasks?
Just make sure I understand the question. So like there are maybe some world models that are conditioned on. So for Genie, right, it's more like an interactive game settings where you can condition on some instructions like moving forward, moving left and right. And then, so maybe the difference is really in the action space. So for robotics, the action space is a lot more precise. It's the robot end effector poses. So it actually requires very detailed model reflecting the effect of executing these actions. Whereas in some of the game applications, like roughly speaking, moving forward and turning left and right, like you could get those pretty easily. So maybe, sorry if I didn't fully understand the question. Are you?
Like we see like a robotics arm moving an eggplant. That's a very specific task. Could we see world models being deployed to generalize across many tasks?
Yeah, so world model is really task agnostic, right? It's only a dynamics model. It conditions on actions, which is some changes in the control space, right? How much force are you applying? How much torque are you applying? And then sort of be able to map that change onto the visual observation change. So it doesn't really have to have a notion of task, as in it doesn't have to condition on language. The task for the world model itself is to accurately predict the next frame. So then like you can really use it for any task, right? If you can predict condition on the deltas in the action space to predict the delta in the observation space, this is generalizable across different tasks.
And I had one quick question about the MLE agent. So it seems like for Kaggle datasets to like be the best human, let's say, you really need to understand the domain of the dataset and do some feature engineering. So I was wondering, is that a fundamental limitation with automating this? How can you use some sort of LLM capabilities or actually explore the dataset without blowing up the context window?
Yeah, that's a great question. So what I've observed is that like the model generally is capable to do things that are human ML engineers are able to do. Like, for example, they will actually propose like different ways to feature engineer. And I think what's really missing is the ability to transform these experiences. So the model could propose different feature engineering techniques, and then it actually runs the experiments with different feature engineering, but it's not quite able to really turn these experiences into kind of like knowledge about the data set, like this actionable from like this gap from like experience to actionable knowledge. I think this is the part that they don't have too much supervision training data for, and this is where they're lacking. So I think for tackling these challenges, there are many different ways to do it. Like, for example, coding, right? Like you can use a frontier model to just generate the code, but really like the training probably should happen explicitly on this process of like, turning experience into actionable knowledge, which might require some prompting, right? Like you need to ask the model to summarize these experiences in certain ways that can help it develop better next step to try, for example. I think this is the part that's really missing. Yeah. Yeah.
Hi, thanks for the great talk. I want to ask a question about the water model robotics part. So my question is, do you think this recipe can generalize or scale to a more complex and realistic setup? Let's say a realistic manipulation setup, you have multi-view cameras, you have proprioception, you maybe have force. But here, I think this is just like an action condition video models. But when you go to a more complex setup, can you think current recipe can generalize? That's my question one. The question two is, for example, when you use the generative editor like Null Blender to add a new object there, how can I know how heavy that object is? The word model seems does not have an understanding about all the space property. How can you see the current limitation and how do you improve this? Thank you.
Yeah, thanks for the good question. So for your first question, yes, so this general action condition future observation generation is actually quite general. So I showed the example of World Gym, but there's work from Google VO Robotics where they trained like also a world model for policy evaluation. And then what they did is like concatenating different views into the same frame and then generating the videos across frames. So the major difference is that basically you can treat all of the different views and put them in the context. And then when you generate the different views for the next step, you actually can attend over all of the views from the previous step to get consistent generations. So I think that part is, I wouldn't say solved because sometimes things still become inconsistent from time to time, but there's definitely a way to sort of align these different frames and put them in the context, different views in the context and get reasonably consistent multi-view generations. And then for the question about there's no force information, there's no state information, I think it's still doable. And in fact, like we had some follow-up current work where we found that like because of a lot of the policies actually do conditional states in addition to observations. For example, pi from physical intelligence, they always conditional states for more accurate predictions. So and in those cases, you can think of like the world model I showed earlier. In addition to predict the video frames, you can have some additional tokens about the state. And then you can, in fact, stuck like whatever additional information you have, whether it's some kind of force information, some kind of sensory information into this additional state. And I guess the question is like, how can we stay general to still be able to train on data set that don't have this information? And then I think maybe we can reserve some tokens for additional, auxiliary information modeling. And then when this information is present, we can just feed them into the pipeline. And then if they are not present, we just treat them as empty tokens, for example. So I do think that they still fit into the framework of action condition future observation generation. It's just whether the observation is images or if it's some auxiliary information about states. So now you can actually roll out a policy that does also condition on this auxiliary information. And then I guess the similar approach probably applies to your example of adding like orange. So if you had in your data set like touch sensors about the robot picking up different objects and maybe from different data sets, the idea is like you're merging all of these information into one model, right? Like almost like a compression in some sense. And now like you have like an initial frame, and if you're trying to predict the states, because it has been trained on states with orange, for example, and maybe you can already kind of generalize to what the touch sensor reading might look like when you try to predict the next frame and the next touch sensor readings.
A follow-up, do you think that could be a data egg and chicken and egg problem? Because to have such model that can understand the face, you have to collect such robots sensory data. But we also don't have such robot sensory data. We would like to world model can generate or evaluate those kind of data. So do you think this approach could be some like potentially chicken and egg problem in the data?
I don't think necessarily, because like you can get you can get somewhat far with just like a pure vision-based policy. Like there are people who are only training vision-based policies, and once you have a reasonably working vision-based policy, you can add your additional sensor readings, and you can automatically, by running the policies, you can get additional data readings. You don't have to get data readings from like sensory readings from teleoperation data, for example. If your teleoperation data, I mean, this happens a lot, like during iterations of a robot lab. Initially, they only bought some cameras, and then like later on, they added some sensors, right? But I think like an easy way is to, okay, train an image-based policy, and now just roll out the policy to collect data with sensor information. And now you can, use this data to train your world model to be more like sensor aware, for example. Yeah.
Thank you.
Yeah.
Building off of some of these previous questions, I work in like neuroscience and neurons and the morphology of them and how those lead to computation. So your work on the system of science agents was very compelling because I saw how you could create like structure, like you can turn text into structure. One of the things that seems to be missing, which is, you're going from 20,000 to 2,000, and then actually the highest level of curation, the full difference is the expert 2060, right? So it seems that some amount of intuition is missing within these models right now. And it seems to be, this is true when we interact with quad code or any of these as well. I'm wondering for physical systems, do you have any ideas how these could be better incorporated such that you're not, you probably want basic assumptions about like how much this material can heat up, or like, that it's not at these crazy extremes, or it's that it's also utilizing some of these like latest benefits in material science when it's defining them.
Yeah, I think the bottleneck to narrow down from the 2000 to 60 is really because there is no data for assessing like synthesizability, or because when we have human expert look at these data sets, there's no tradition of having them like write down the exact reasoning for why every single structure is looking good or not looking good. But that doesn't mean that we shouldn't be starting to collect these data sets, because we know that usually for the part that LLMs are not doing well is because we don't have data for it. So I think it's more of an inspiration for like people working in AI for science for like what data to collect as the next step. And then usually, I mean, there's kind of like some research on like trying to train some kind of reasoning models given structures to talk about the structures, and maybe from research papers there's kind of like a lot of reasoning about different structures. So I think synthesizability is something that's kind of missing from these papers because of the dataset bias. Because usually the paper only talks about successes and they don't talk about failures. So as a result, like the reasoning is highly focused on successes and less about this is gonna fail because it's not realistic enough. So I think it's more of a data set problem. And I think from the computational side, like there are these additional like all of these tools that are automatable, and then usually the decision making is based on some information from these tools combined with human knowledge. I think that again, it does seem like the data is relatively cheap for computing these properties, but then like the sort of going from those properties to the final decision of are we going to synthesize this material or not, that's kind of like the missing part of the data. So I would say it's more of like a data problem that we should like start collecting it day one, like now. Yeah.
Okay.
Yeah. Yeah.
Maybe this is related to what you just said. So for the first two scenarios, you mentioned how you can use frozen LLMs or frozen language models to retrain your agent via policy optimization. In the third scenario, you talk a little bit about how you can retrain your agent with the feedbacks.
Yeah. So definitely, I think right now there is the research on, because once you remember the hierarchical tree I showed for like material science, like once you have this tree and you actually do end up running a bunch of computational tools to compute the properties, and from that you actually do have reward signals depending on what you want to optimize, whether it's band gap or properties like conductivity, energy, and so on. Like you can sort of use you can use that to update the parameters of either the diffusion model or even the language model. Or if you have some kind of, nowadays people talk about omni models that can predict, discrete tokens and continuous values. But you do have like the rewarding information for doing RL. I think the question is, the bottleneck there is usually more like a domain gap, because to run these computational tools, you need someone from the science side, or even sometimes like license issues, you need some kind of license to run some kind of BFTs or knowledge gap. And so like the reward model isn't extremely accessible. And like this is also again like when the world model aspect comes in, which is, I mean, you can predict, not just the dynamics, but also the reward information. So every time you do some computation, you can, save those data so that you can train like a structure to property machine learning model. And I think people have pretty good model for machine learning force field for predicting the formation energy from any structures, just because every single structure has a formation energy, right? So, and as a result, they have a lot of data for training this model. And right now, the force field prediction is already pretty accurate for even generated structures. But for other properties, maybe sometimes if there's not enough data with that particular property being measured or computed, then it could be a little harder to train. But still, like the data set will accumulate itself, like they're not going away. And more and more computations are being run. And eventually we will reach a point where we have enough data to train these low-cost reward models that doesn't require these extended computational processes that we can use these cheap reward models to run our fine-tuning for the higher level formula and structure prediction. Yeah.
I have a question about the world models for physical physics part of the talk. So I remember there was an article that came out in 2025 by Sergey Levin. I think it was called like Sporks of DGI, like a pretty popular one. And he mentioned how as you scale up robot foundation models to be larger and larger, you sometimes run into the issue of like overfitting to the simulator if you're training in simulation. I think he was talking more about the case of like physical simulators rather than world models. But do you think that issue still applies for world models? Like as you scale up your robot foundation model, is there an issue of overfitting to the simulator and not being able to transfer to reality? Or is that kind of solved with the case where, as you roll out things in the real world more, you need to update your world model just as you update your policy? And is that fixed?
So what you said is like one solution. I do think that like right now they're like world models are not perfect, and oftentimes they do have hallucinations, and also the reward model are not perfect. I think like one of the active area of research for using world models to do maybe RL training for foundation robot models is that the world model is the reward model, because the reward model is usually some vision language model, and vision language models are trained on real world data, and there's only successes in real world data because people, when we do anything, they're successful. So they don't have as like a good ability for detecting subtle failures or for assigning progress reward for completing tasks. And when there's some failure in the reward model and also some hallucination in the dynamics, then like, of course, the policy is going to be exploiting kind of like the issues of the world model. I think that maybe what you're saying about additional data and improving the world model is the more forward-looking approach, because if we have a parametric model about the dynamics, then the model can only get better with more and more data. Whereas the physics-based simulators, it's limited by our knowledge of how physics can be simulated, and we don't know how to simulate some of the things like soft object interactions and so on. But there will be more and more data collected. So in some sense, I am pretty hopeful for the world model, and I do think that world model is receiving a lot of skepticism because of like generalizations or these hallucinations. But I just want to remind us, like the model like you looked at today, when you scan the QR code, it's like a 600 million model, right? So we're doing some research on like looking at scaling up both the data set size and also the model size. So we've trained like models of like 2 billion parameters, 4 billion parameters, and 8 billion parameters, and we just see that because for action condition future frame prediction models, you actually have very good evaluation metric. You just look at the generated frame and then the ground truth next frame, right? And so we look at these metrics, and like basically the larger model, the better the performance. And even the AB model, we don't see any overfitting quite yet. So I think there's also a lot of interesting research around pre-training the best world model on all of the action-rich manipulation data from humans, from robots, from the real world of any morphologies, to see how far we can get from the scaling side. Maybe some of the problems may just go away with scaling, right? That's kind of like the hope, as opposed to like trying to enforce some kind of physics priors, which could be difficult. Yeah.
As like a small follow-up, like on the scaling side, is there information on, or is there enough information? Have we seen sort of trends for how the scaling is operating yet for world models as compared to like simulators? Like, is it looking better, I suppose, for world models as a whole?
I'm not sure how much scaling study has been done for physics-based simulators. Maybe you're talking about like if we train the policy in the physics-based simulator. So for that, I think we're pretty far away. Like I think World Gymnast is like among one of the first ones to try to actually run RL training of the policy in a learned video-based world model for these more pick and place based tasks. So I think like the results, at least on the policy side, like how policy reacts to different sides of the world models, that study hasn't really quite happened. But there are quite a few work, like my group is working on this, and I think maybe the Dream Dojo paper that recently got released from NVIDIA was also looking at, they trained like a model of 2 billion parameters and another model of 14 billion parameters, and they show like the 14 billion parameters generally have better metrics in terms of action condition future frame generation. So there's definitely signals of larger model performing better for next frame prediction. And hopefully that should translate to better policy performance when we run RL. Yeah.
Great, thanks everyone for the questions. I think we're at the end. So if you have any further questions, maybe contact Sherry.
Thank you.